Hi EDCON, here is Gluchowski from Meta Labs, and I'm here to talk about layer 2 scaling, zkRollup, and our scaling protocol called zkSync, which implements zkRollup. So why scaling? It's obvious to all of you that the Ethereum prices or gas prices are getting outrageous. Cost like $3 to send a $1 ERC20 token transfer. More complicated transactions are even more expensive. And the reason for this is pretty clear. Price is determined by supply and demand. Ethereum is in high demand with the transaction space limited by block gas limit, and we see that it's getting consistently used, and projected usage is probably going to be even higher when more people, potentially millions of people, are going to jump onto blockchain and become users. And the problem is actually very old. It was previewed by Satoshi back 10 years ago. And it's been really hard to solve. Like, we had 10 years of research, which led us here where we still cannot properly solve layer 1 scaling. Why is that? Why is it so hard to scale blockchain? The reason, in my opinion, is that the value proposition of layer 1s is resilience. That's the most important thing for blockchains, for decentralized blockchains. Ask guys from Libra and Telegram why they didn't launch. They could not defend their projects. They had technology, they had the users, but they could not just push through because they were not resilient enough. The reason, or the way Ethereum and Bitcoin reach resilience is decentralization. We have thousands of full nodes verifying the blockchain. All of these nodes are equal. There is no single point of failure. So it's really hard to control all of them because they are spread all across the world with different jurisdictions, different countries. You cannot just impose one rule on all of them. This is very valuable, but this has a consequence. If you want to have network consisting of heterogeneous nodes with like all being equals and peers, it means that you cannot trust anybody because they can be malicious. Anybody can join such a network. So you have to rely on the principle of don't trust, verify. You have to actually execute every single transaction in every single layer 1 node to keep the system secure. Which brings us to the definition of scalability. Simply increasing throughput by extensively raising the bar higher, let's say by increasing the Ethereum block gas limit, would not increase scalability because it would also increase the requirements on the full nodes. And so less people can run them, and the network will become less decentralized and less resilient. So you want to improve throughput without increasing the load of an average node, and this is what we call scalability. It turns out there are two ways to do this. You either verify not every single transaction but less. So maybe you split your accounts in different shards and you only verify it, like everything with what happens in your shard. And this is the approach layer 1s themselves are taking with ETH2, NEAR, and other blockchains who are doing multi-sharding technology. Or you do something sophisticated and you execute or you verify a larger amount of transactions spending the same amount of computational resources. So for the second way, the compression, we have something like zero knowledge technology, which is very recent and only became mature in the last year. Sharding is more popular. It actually, the layer 2 world started with sharding approaches such as payment channels, which is an ultimate sharding solution where you have a payment channel between two parties, and these two parties only need to monitor the state of their channel on layer 1. They can transact, nobody else cares about their transactions. They can update the channel state off chain many times, but it's not very convenient because you don't want to transact with one single person. You want to send money to like arbitrary recipients. So then they evolved into payment networks such as Lightning. But that brought additional problems because you needed capital requirements, like you needed to lock a lot of capital in this network to be able to route transactions from arbitrary user to arbitrary user. And you had to undergo security risks for running these Lightning nodes because you have your keys on hot wallets and online machines, which can be easily stolen. So it evolved further into things like side chains, where you sacrifice some of the security because you still verify less transactions by the fact that like you delegate verification to a small number of validators who have some kind of stake. But of course, it has like very limited applications. So then things like Plasma emerged, where anybody could challenge those validators or one single validator. And it further evolved into optimistic rollup, which we will cover a bit later. But there's actually we created a framework to evaluate all the solutions, and I'm going to post a link under this video, a framework of questions where you can just go and check, look at various layer 2 solutions from various angles. But you will see that the nastiest problem in all of them is data availability. So if we look at all the solutions, most of them keep the data off-chain, and this leads to problems. Except for layer 1. This is a bit incorrect. Like layer 1 is, of course, everything is on-chain, but layer 2 solutions, all the red ones have it on layer 2, have it off-chain completely. So it is always possible to withhold the data, and then you have to react to the situation, and you need to build very complex game theoretical and technological things around that, and you have the mass exit problem in Plasma and so on. But you have two technologies, optimistic rollup and zkRollup, so we can call it just rollup technology, which puts all of the data on chain and solves most of these problems. So with rollups, you actually reach levels of security very, very comparable to the mainnet, and also levels of usability. It comes at a cost. The cost is that your scalability boost is capped at around 100x compared to mainnet. So we cannot exceed that. We still need to put some data on chain. But on the other hand, rollups are capable of reaching up to 3,000 transactions per second. And the cost, if we take the current Ethereum transactions at like a couple of dollars divided by 100, you will get a couple of cents. It's probably okay. So like if your application, if your protocol is okay with like 10 cents up to $1 fees for transaction, you probably don't need anything else. You're probably best served by rollups. So I really recommend looking into them. It's interesting to compare optimistic and zkRollup. They are very similar. They are both commit chains. They keep only the fingerprint, cryptographic fingerprint of the state in the contract on the mainnet. And they have blocks. These blocks change the state and record in the new cryptographic fingerprint of the new state in the same contract. They are different in the ways they secure the validity of state transitions. With optimistic rollup, the operator is allowed to make any state transition they want, but anybody who sees a problem with this state transition can challenge them. So you have some period of time where you can submit a fraud proof and revert all the changes from the last valid checkpoint. With the zkRollup, it's the opposite. The validator is required to submit a validity proof in advance. So first you produce a validity proof, and only then are you allowed to make a state transition. And as you can see on this comparison, it creates a number of advantages for zkRollup. For example, security of zkRollup does not depend on any validator or actually on anyone doing any work. It is completely passive. With optimistic rollups, you have an assumption that at least one party at all times is monitoring what is happening on the rollup and is honest. So one of the parties who monitor the activity must be honest for optimistic rollup to function. And realistically, it must be a validator, because only validators are incentivized to actually do some work. If they stop doing this work, then malicious party can steal all the funds in the rollup. Even if they do this work and they spot the fraud, they still need to submit a fraud-proof transaction. And if they fail to do this, or if the transaction fails to mine because the network is congested, or because there is some failure in sending nodes and they run out of ether, or maybe because miners are colluding or being bribed, then all of the funds in the rollup can be lost. With zkRollup, you don't have this problem. If you don't have, like, if your validity proof fails for some reason, you just keep trying until you generate a proper one. And during that time, the funds are safe. If nobody generates state transitions, people can always exit through layer 1. Further, this aspect of fraud proofs makes the usability of zkRollups much more delightful in terms of normal exits, because in optimistic rollup, you need this long period of time for everybody to be able to spot the fraud and to submit the challenge. With zkRollups, as soon as you have the zero-knowledge proof of validity, which takes minutes, you can immediately exit. With optimistic rollups, it's considered secure at around 1 week at least. Finally, because in zkRollup we use zero-knowledge proofs, and they have this nice zero-knowledge aspect that you don't need to disclose everything for proving validity, we can implement privacy naturally, easily, and cheaply. Whereas in optimistic rollup, the privacy is going to be at least 1,000 times more expensive. So both zkRollups and optimistic rollups are in development. zkRollups are live with zkSync and loopring. You can try them on mainnet. They are fully functional. So as you can see, there are lots of advantages to zkRollup, except for one. Optimistic rollups are theoretically easier to construct in such a way that allows portability of existing Solidity code or existing EVM bytecode. With zkRollup, you would need to, if you want to deploy smart contracts, you need to rewrite them or adjust them from the code which currently exists, which takes some work. It's not a part of protocol, but it's something which you need to take into consideration. So if you just want to do transfers, zkRollups are available today. If you want to do smart contracts, you will have to do some slight changes. So we actually have another article which dives deeper into this comparison of zkRollup versus optimistic rollup. I'm going to put a link to this under the video as well. Okay, so let's talk about zkSync, our zkRollup protocol implementation. Here is a slide from our Reddit great scaling bake-off submission. We were one of the something like 20 projects who made submissions, and I think one of a very few who actually fulfilled 100% of Reddit requirements. We can handle up to 3,000 transactions per second on today's Ethereum mainnet. It's not yet implemented. Right now, the tested facility was 800 transactions per second, but it will take us short time to make small minor optimizations in the block aggregation to get to 3,000. It has security comparable to mainnet. Operators can never do anything wrong with user funds, not freeze them, not steal them, not corrupt them in any way, not confiscate, nothing. It's going to be decentralized. We're going to have a consensus among multiple validators, which is going to be governed by token holders in zkSync, and it's built around user centricity. It's very we put a lot of effort into building zkSync as a very usable application or a usable protocol. Right now, what you can do with zkSync is Ether and ERC20 token transfers. And we support meta transaction. We natively support multisig. You can send Ether to any Ethereum address, even if it's a smart contract or some account which you never interacted before with. And you can also interact with smart contracts. So smart contracts with some funds in the zkSync can have some interactions with them. They can set multisig, like they can appoint custodians, or they can force withdrawal funds and so on. So you can build some interesting complex interactions around that. And zkSync version 2.0 will support smart contracts with a programming framework called zkSync, which we're currently developing, which you can also already try and start building programs. You do not need to know anything about zero knowledge proofs, math, any complex things. You just have to observe a few simple rules how you write these programs, but they are essentially the same as you would write them in Solidity. So you define your state, you define your public, private functions, and you're good to go. If you know Solidity, you can learn zkSync in essentially one day. If you know Rust, it's going to be very familiar as well. So we took the best elements from Rust and Solidity and combined them together. That's it. You can follow us on Twitter. Or you can go to zkSync.io and try out zkSync on mainnet or testnet. And now I'm going to show you how it actually works. So I'm going to go to my wallet, and I can connect any Web3 enabled wallet like MetaMask. So I'm going to click on MetaMask, sign a message here to log in. I'm in my account. I got some balances here. I can deposit some more. Let's go and make a deposit of some Ether. 0.1 deposit. I'm gonna confirm it. It's in transactional layer 1. We can follow it on Rinkeby. It's pending, so we're not gonna wait. We're just gonna go and make a transfer in zkSync with existing balances. So for a transfer, I'm gonna go to a different browser, open MetaMask, create a brand new account. I'm gonna call it account 4. Click create. Copy the address of this account. It has no Ethereum history, no history on zkSync. Gonna go back to Brave and make a transfer of, let's say, 100 USDT to this new address. Click transfer, sign a message, it's sent. Now I'm going back to Chrome, and now I'm connecting with MetaMask. So it will ask me to sign a message. It's a wrong account. Sorry, I need to switch. I need to click connect here. And now I'm on the right account. I'm just signing the message. It's open, and I already got my 100 USDT. So I can go see from whom I got it and send some money back. I need to unlock the account. That is to say, I need to set my private key for zkSync network, which is going to be used for zero knowledge proofs. So I'm just signing a message, and it's instantly confirmed. And I can send some tokens back. Clicking transfer, send. So it's immediately out. If I go back to Brave, I will see this incoming transaction here. All the transactions with a single check mark are pending. That means they will be, they are instantly confirmed, but they are not yet finalized. Transaction is final as soon as you see this double check mark. That means that we generated a zero knowledge proof, submitted it to Ethereum, to the smart contract of zkSync, and it's verified. And once you have this double check mark, this transaction or this balance is enjoying the same security properties as mainnet. So you can withdraw it no matter what, even if you go offline for a year and come back. Yeah, so that's it. Thank you very much.